We have inherited a theory of knowledge that mistakes its own historical correction for the completion of epistemology. The modern scientific method arose against real failures. Repetition had hardened into authority, interpretation into doctrine, and tradition into a means of preserving conclusions after the reasons for them had been forgotten. Skepticism was necessary. It demanded tests, formal representations, and results that could survive beyond the prestige of the person asserting them. But a corrective method is not automatically a complete method. Modern science increasingly treats the instruments of skepticism as foundations of knowledge. Staged experimentation is preferred to naturally embedded observation. Mathematical abstraction is permitted to stand where experiential understanding is absent. Repeated numerical stability becomes constancy, and constancy is projected outward as though stability within a measured domain established universality. When projection fails, the failure can be absorbed retrospectively through another factor, qualification, interaction, or scale of description. Today we argue that precision is not explanation, reproducibility is not necessity, and a formula that continues to work is not yet an account of why the relationship must hold, what maintains it, or where it ceases to hold. The alternative begins from consistency. Reality is not made orderly by our recognition of order. If recurrence can be recognized, experiments can distinguish outcomes, and equations can retain usefulness, then prior relational structure must already constrain what can occur. 3 distinguishable elements are proposed as the minimum required for a dynamically intelligible system. 1 supplies initiatory pressure, a 2nd countervailing resistance, and a 3rd the context or boundary condition within which their relation becomes intelligible. 2 elements can be compared or made proportional, but they cannot internally specify the condition maintaining their relation. The 3rd makes balance, mediation, closure, and transition describable. From this follows an 11-stage progression. The experiential cycle consists of repetition, interpretation, and tradition. The skeptical cycle consists of testing, abstraction, and constancy. The alignment cycle consists of pattern matching, inference, and coherence. Association then determines what should be preserved from all 3 cycles, and integration unifies the 9 capacities into a complete process for obtaining, applying, validating, preserving, and teaching knowledge. This is better understood as rediscovery than invention. Ancient systems repeatedly organized knowing through triadic relations: knower, known, and relation; premise, mediation, and conclusion; witness, confirmation, and judgment. Ancient philosophers like Aristotle and Pythagoras, myths, scriptures, Vedic thought, and esoteric traditions, among many others, all preserve examples of a relational habit of mind, in which relationships are made intelligible through mediating conditions rather than reduced immediately to isolated objects or unexplained coefficients. The claim is not that these traditions possess this exact model. It is that pattern recognition requires familiarity with pattern, and much of human intellectual history can be understood as an extended effort to preserve recurring relational forms in stories, arguments, symbols, teachings, and models. The modern problem is therefore not simply that knowledge has become abstract, but that it has become fragmented at the same time that familiarity with relational patterns has diminished. Scientific disciplines accumulate increasingly precise knowledge of particular objects, while becoming progressively less able to relate their findings across domains. Older traditions often possessed far less quantitative information, but devoted sustained attention to recurring structures of causation, balance, conflict, mediation, transformation, and restoration. Their stories remain useful not because their objects must be taken literally, but because changing characters and circumstances can instantiate the same underlying patterns. Learning to recognize those patterns is itself an epistemic skill. The more varied examples one encounters and considers, the easier it becomes to recognize the same relation when it appears in an unfamiliar context. Scientific formulas, constants, experimental results, inherited practices, historical failures, myths, philosophical arguments, and ordinary experience can all become data for a more encompassing inquiry. A successful formula records a relationship that remained stable under certain conditions. A failed prediction identifies a boundary that was misunderstood. A traditional story can preserve a relational pattern whose objects differ completely from those encountered in a laboratory or institution. The task is to compare these manifestations, identify the elements occupying equivalent relational positions, and determine which patterns remain coherent as the objects and scales change. Knowledge then progresses not simply by accumulating additional facts, but by increasing the number of contexts in which the same underlying structures can be recognized. The demand here is therefore not that accumulated science be discarded, nor that inherited traditions be restored as authorities. It is that both become material for a more demanding form of comprehension. A result is not understood merely because it can be repeated, fitted, formalized, or reproduced. It becomes understood as relevant elements are identified, possible relations constrained, incompatible interpretations eliminated, and consequences inferred without arbitrary additions. The goal is a culture of knowledge in which people become increasingly familiar with the patterns through which reality organizes itself, increasingly capable of recognizing those patterns in new circumstances, and increasingly confident in inference because that confidence rests upon coherent relational understanding. Knowledge began with the recognition that reality repeats. Skepticism taught us that our interpretations of those repetitions can be wrong. The next development is to understand the structures that made the repetitions, the corrections, and eventually the comprehension possible in the first place. Any account of knowledge must begin before there is a theory, a method, or even a settled interpretation. It begins with contact. Something happens, something is retained, and something happens again in a way that can be recognized as belonging with what came before. This first movement is not ignorance waiting to be rescued by formal thought. It is the earliest positive encounter with order. The experiential cycle therefore begins with repetition, because the possibility of knowing depends first on reality, presenting distinctions that can recur within a sufficiently stable context. At this stage, nothing has yet been explained. The point is more basic. Recurrence makes a world intelligible enough to enter thought at all. Only after an occurrence can be recognized as related to another occurrence can meaning, expectation, practice, or explanation develop. Repetition is therefore the source condition for the first epistemic cycle, and the question it leaves behind is the one that drives the next stage. Once recurrence has been recognized, what are we to make of it? The three subcomponents are present occurrence, retained occurrence, and shared context. Present occurrence is what is encountered now. Retained occurrence is what remains available from an earlier encounter. Shared context is the condition that allows the two to be recognized as instances of the same kind of event, rather than as unrelated happenings. Repetition is the first source of knowledge because nothing can be interpreted until something can be distinguished as recurring. Before explanation, there is recognition. A sound is heard again. A season returns. A material bends in the same way under a familiar load. A person repeats an action and encounters a similar consequence. These experiences establish that reality is not presenting itself as an undifferentiated sequence of unique events. Some relations endure long enough to be recognized. The importance of shared context is easy to underestimate. Two events do not constitute repetition merely because an observer can place them next to one another. They must be comparable. The same visible motion can result from different structures. The same numerical output can arise from different processes. The first epistemic discipline is therefore not counting recurrence, but determining what makes recurrence meaningful. Repetition is already relational because the present, the retained past, and the common context have to coexist before recurrence can be identified in the future. Traditional knowledge systems were strong at this stage. People who had to live directly with weather, animals, soil, construction, navigation, health, and social behavior accumulated extraordinarily fine-grained recognition of recurrence. Their knowledge often lacked formal decomposition, but it was anchored in consequences that could not be delegated to a symbolic model. A builder who misunderstood stone did not publish an elegant correction. The structure failed. A navigator who misunderstood seasonal patterns did not merely refine a parameter. The journey was endangered. Repetition therefore carried practical weight. Its limitation is equally important. Repetition does not reveal necessity. 10 successful occurrences do not tell us which relationship among the circumstances produced the success. A recurring sequence may be causal, conditional, coincidental, or generated by a third element that has not yet been distinguished. The experiential error begins when recurrence is treated not as information, but as explanation. Alignment preserves repetition while changing its status. Recurrence is indispensable evidence that some structure persists. It is not proof that our interpretation of that structure is correct. The task is to retain the informational richness of naturally embedded experience, without allowing familiarity to substitute for relational analysis. This changes what observation means. Observation is not a passive collection of data points awaiting a mathematical law. It is the disciplined recognition of stable distinctions in context. A measurement stripped of the conditions that made it meaningful can be more precise and less informative at the same time. The first responsibility of knowing is therefore to identify what actually recurs, what is merely similar, and what contextual element makes the comparison valid. Repetition begins the progression because it gives us our first warrant for believing that comprehension is possible. If nothing recurred, there would be nothing to learn. The world would be a sequence without structure. That experience is not our experience. We encounter persistence, recurrence, and recognizable relation everywhere. The error of traditionalism was not believing in consistency. Its error was believing that repeated experience had already explained the consistency it revealed. Repetition establishes that something recurs, but recurrence alone cannot tell a knower what the recurrence means or how to act upon it. The second stage begins when a recurring distinction is no longer merely noticed but treated as significant. This is the movement from recognition to use. Interpretation is therefore not an optional layer added after observation. It is the process by which repeated experience becomes guidance, expectation, warning, opportunity, or explanation within lived activity. That advance also creates the first internal vulnerability of knowledge. Once experience has been interpreted, later experience is encountered through the expectations the interpretation has produced. The same mechanism that makes learning cumulative can make error cumulative. Interpretation must therefore be understood both as the indispensable conversion of recurrence into meaning, and as the point at which a useful reading of reality can begin reinforcing itself beyond what the original observations warrant. The three subcomponents are recognized distinction, assigned significance, and resulting expectation. Recognized distinction is the feature made visible by repetition. Assigned significance is the meaning attached to that feature. Resulting expectation is the anticipation that follows once the feature has been interpreted. Repetition by itself cannot guide action. Something has to be made of it. Interpretation is the process by which recurring distinctions become useful. Clouds become signs of rain. A sound becomes evidence of strain. A behavior becomes an indication of trust or danger. A recurring sequence becomes a practical expectation. Through interpretation, experience stops being a record and becomes a guide. The structure is reinforcing. A recognized distinction encourages a particular meaning. That meaning produces an expectation. The expectation directs future attention toward confirming or disconfirming features, and those features strengthen the original distinction. This is how practical knowledge can become sophisticated without formal theory. A craftsperson may know exactly when a material is ready without possessing a symbolic account of every microscopic process involved. The interpretation is embedded in repeated interaction with the system. But reinforcement also explains the birth of dogma. Expectations shape attention. Familiar categories shape memory. Once an interpretation has become useful, ambiguous experiences tend to be organized around it. A community can therefore become increasingly confident in an interpretation precisely because the interpretation has become the filter through which new experience is recognized. This is not a defect unique to ancient or traditional thinking. Modern formal systems do the same thing at another level. Once a theory defines the relevant variables, instruments are built to measure those variables, experiments are designed to manipulate them, and results are reported in the theory's vocabulary. Interpretation never disappears. It becomes less visible because it has been built into the apparatus. The proper response is not to abolish interpretation. There is no uninterpreted knowledge. The response is to make interpretation explicit enough that it can itself become an object of analysis. What distinction has been recognized? What significance has been assigned to it? What expectation follows? What alternative significance could produce the same observed recurrence? These questions prevent the practical success of an interpretation from being mistaken for proof of its completeness. Interpretation is the first stage at which knowledge is applied. It connects what is observed to what should be done next. That function will never be replaced by mathematics, because application always requires meaning. A numerical prediction has no practical content until someone knows what the number refers to, why it matters, and what consequence follows from acting upon it. The experiential system therefore contributes something essential that skepticism cannot erase. Knowledge must become intelligible in lived relation before it can become useful. The later stages will discipline interpretation, abstract it, test it, and eventually constrain it through pattern. None of those operations remove the need for meaning. They exist to ensure that meaning is earned rather than merely inherited. Interpretation allows one person to act on recurring experience, but knowledge that remains bound to one person's memory disappears with that person. The third stage arises from the need to preserve what has proved useful. A community converts successful interpretations into practices, teachings, warnings, stories, procedures, and expectations, so that accumulated experience can survive the circumstances in which it was first acquired. Tradition is therefore the completion of the experiential cycle. Recurrence supplies the information, interpretation supplies its meaning, and preservation gives that meaning continuity. The very success of this solution creates the problem that will eventually call forth the next cycle. What can be transmitted most easily is the conclusion or practice, not the entire history of relations through which it became intelligible. Over time, preservation can make an interpretation appear authoritative because it has endured, even when the conditions that originally made it useful have changed or were never fully understood. Tradition preserves knowledge, but it can also preserve the limits of the interpretation that produced it. The three subcomponents are stabilized experiential knowledge, preserved practice or teaching, and inherited expectation. Stabilized experiential knowledge is an interpretation that has survived enough use to become dependable. Preserved practice or teaching is the means by which that knowledge is transmitted. Inherited expectation is the confidence carried by the recipient that following the preserved practice will reproduce its result. Tradition is often treated as the enemy of knowledge because inherited belief can resist correction. That criticism begins too late. Before tradition becomes dogma, it is a solution to the problem of memory. No civilization can advance if every individual must personally rediscover every useful relation. Knowledge must persist beyond the person who first acquired it. Technique must become instruction. Interpretation must become language. Successful practice must become reproducible practice. The first great achievement of tradition is therefore compression across generations. A long history of trial, adaptation, and experience can be carried forward in a short rule. Build this way, plant at this time, do not combine these materials, approach this situation in this order. The recipient may not possess the full experiential path that produced the rule, but the rule can preserve the result. The danger enters through exactly that compression. What is transmitted is rarely the entire relational history. Practice and explanation become fused. A useful procedure may be preserved along with a mistaken account of why it works. A warning derived from a particular boundary condition may be universalized after the boundary condition has been forgotten. A relation that was once tested by consequence may become protected by authority after the original conditions can no longer be reconstructed. Traditionalism results when preservation becomes validation. The fact that a belief has endured begins to count as evidence that the belief must be true. The social mechanisms required to transmit knowledge then become mechanisms for defending interpretation. Elders, institutions, texts, guilds, schools, and rituals can all become repositories of accumulated success and barriers against correction at the same time. The modern response was to negate tradition. But the function of tradition cannot be discarded. Modern science has traditions of its own: textbooks, canonical methods, disciplinary vocabulary, standard models, accepted constants, peer review conventions, and institutional credentialing. The form changes, the preservation problem remains. Every knowledge system must decide what to transmit, without requiring every learner to repeat the entire history of discovery. Alignment therefore asks a different question: what should be preserved and in what form if preservation is not allowed to substitute for understanding? The answer is that instruction should preserve reconstructible relations, not merely authoritative conclusions. A learner should inherit enough of the path to see why the practice works, what conditions make it applicable, and what observations would require revision. Tradition completes the experiential cycle. Repetition provides information. Interpretation gives it practical significance. Tradition makes that significance durable. The cycle's failure is not that it contains no knowledge. It is that it can no longer distinguish knowledge from the interpretation used to carry knowledge forward. The next cycle begins when contradiction becomes strong enough that preservation can no longer absorb it. The experiential cycle reaches its limit when preserved interpretation encounters experience that it cannot accommodate without strain. An unexpected result, an unfamiliar condition, or a rival interpretation exposes the difference between a practice that has often worked and an account that must be true. At that point, repetition can no longer settle the dispute, because the disagreement concerns what the repetitions mean. A new epistemic pressure is required: resistance to the inherited interpretation itself. Testing is that resistance. The skeptical cycle does not begin because experience has become worthless. It begins because experience has generated conflicting interpretations that ordinary repetition cannot resolve. The test deliberately creates a contrast capable of forcing those interpretations apart. Skepticism is therefore historically and logically secondary to experiential knowledge. It is a corrective response to the first system's inability to distinguish what has been preserved because it is true from what has been preserved because it has usually worked. The three subcomponents are contested claim or anomaly, constructed test conditions, and skeptical determination. The contested claim or anomaly is the point at which inherited interpretation encounters resistance. Constructed test conditions are deliberately arranged circumstances designed to distinguish competing explanations. Skeptical determination is the conclusion drawn from the contrast produced by those conditions. Testing begins as liberation. When tradition says that something is so because it has long been treated as so, testing asks what would happen if the claim were forced to distinguish itself from alternatives. This is one of the great achievements of skeptical thought. It recognizes that repetition can preserve error, and that interpretation can reinforce itself. A belief deserves more than familiarity when consequences depend upon it. The power of testing lies in discrimination. Ordinary experience presents many elements at once. A controlled test attempts to change one relationship while holding others sufficiently stable to reveal which distinction matters. This can expose causal dependencies that tradition could only associate through recurrence. It can also reveal that two phenomena believed to be connected are not connected in the way inherited interpretation assumed. But testing necessarily stages reality. The experimenter chooses what to vary, what to hold fixed, what to measure, what to ignore, what counts as noise, and what outcome will be treated as discriminating. The experiment therefore does not escape interpretation. It relocates interpretation into the design of the experiment. The more controlled the environment becomes, the more important it is to understand which natural relationships have been removed along with the apparent noise. The skeptical error begins when testing ceases to be a corrective instrument and becomes the definition of legitimate knowledge. If a relationship cannot be isolated experimentally, it may be treated as speculative. If an element cannot be measured with available equipment, it may be treated as negligible. If a phenomenon changes when removed from its natural context, the context itself may be dismissed as confounding complexity rather than recognized as part of the system. This is especially dangerous in systems with thresholds, feedback, or context-dependent interactions. A small effect observed under isolated conditions may occupy a decisive position in a larger reinforcing relation. A factor that appears negligible because it varies little in the laboratory may become dominant when another component crosses a boundary. Testing can therefore produce high confidence about a narrow state while revealing very little about transitions outside that state. Alignment preserves the skeptical discipline of testing, but changes its purpose. The best test is not the one that most cleanly produces a number. It is the least disruptive observation or intervention capable of distinguishing between remaining relational patterns. Testing becomes subordinate to inference, rather than a substitute for it. The proper question is no longer simply, what happens if we do this? It is, which possible relation would this observation eliminate? That change forces the investigator to reason about the structure before acting upon it. In high-consequence systems, this is not philosophical refinement. It is the difference between learning from a bounded test and learning from a catastrophe. A successful test can separate competing claims, but its result is still tied to a particular arrangement, observer, instrument, and moment. If skeptical correction is to accumulate rather than remain a series of isolated demonstrations, the distinctions produced by testing must become portable. Abstraction arises to solve that problem. It converts experienced and measured differences into representations that can be compared, manipulated, communicated, and reused beyond the setting in which they were first obtained. This is the point at which skeptical inquiry gains enormous reach. It is also the point at which the relation between reality and its representation becomes a permanent epistemic problem. A symbol can travel farther than an experience, and a formal model can coordinate more information than unaided interpretation can hold. But the greater the power of the representation, the easier it becomes to mistake consistency within the representation for comprehension of the relations. The representation was created to describe those relations, not replace them. The three subcomponents are measured distinction, symbolic representation, and formal model. Measured distinction is the difference or quantity isolated through observation or testing. Symbolic representation is the conversion of that distinction into a number, variable, category, or mathematical term. Formal model is the organized system that relates those representations to one another. Abstraction answers the problem created by local experience. A result that exists only in the memory of the observer cannot easily travel. Symbols make distinctions portable. Numbers permit comparison across scales. Equations compress repeated relationships. Models allow people separated by language, geography, and experience to manipulate the same representation. This power is so great that the representation can become more cognitively real than the phenomenon. Once a model has been built, new observations are increasingly collected in the categories the model already provides. Instruments are designed to measure its variables. Deviations are reported in relation to its expectations. The model begins not merely to describe what is observed, but to determine what counts as an observation worth making. The danger is representational closure. A formal system can remain internally consistent while progressively losing contact with experiential meaning. Mathematical objects can be introduced because they preserve the equations, even when the objects have no direct experiential correlate. More structure can then be added to reconcile new observations with prior formal commitments. The result may become increasingly sophisticated while the path from symbol back to relation grows increasingly obscure. The problem is not that abstractions are unreal. Many relations cannot be comprehended without abstraction. The problem is allowing formal necessity inside a model to stand in for demonstrated necessity in reality. A symbol may represent an unknown relation, a compressed set of relations, an idealization, or a calculational convenience. Unless those possibilities are distinguished, the formalism can conceal ignorance while appearing to eliminate it. This is where constants, tensors, manifolds, fields, dimensions, and other mathematical constructions must be treated with epistemic discipline. Their usefulness does not by itself determine their ontological status. They may describe real structure, approximate real structure, compress unresolved structure, or provide a coordinate language for relating measurements. The question is not whether the mathematics works. The question is, what relation in reality the mathematics has earned the right to represent. Alignment, therefore, preserves abstraction as a language while refusing to let the language become its own standard of truth. Symbols must remain recoverable into measurable or inferable relationships. If a model requires an element that cannot be directly perceived, the justification must come from the constraints its presence resolves, and the consequences that follow from that resolution, not from the convenience of keeping the existing equations intact. Abstraction is indispensable for communication and calculation, but it should increase our ability to articulate relationships rather than our tolerance for unexplained symbols. Its success should be measured by how much structure it makes intelligible, not by how much complexity it can absorb without contradiction. Abstraction makes knowledge portable, but portability creates a practical need for stability. Once experience has been translated into symbols and formal relations, some quantities must be held sufficiently steady for those relations to be reused. This is the legitimate achievement of constancy. It does for the skeptical cycle what tradition did for the experiential cycle. It stabilizes what has been learned so that knowledge can travel. The more relations that can be reduced to dependable coefficients, ratios, and reference values, the more widely formulas can be applied without reconstructing the entire system each time. That economy is not a mistake. It is one of the principal reasons modern science and engineering can coordinate complicated activity at all. The difficulty begins only when a successful stabilizing device is promoted into a final account of why the relation is stable. The three subcomponents are observed repeatability, invariant parameter, and successful portability across tested contexts. Observed repeatability is the recurrence of a measured relation. Invariant parameter is the value used to summarize that recurrence in a form that can be carried into calculation. Successful portability is the continued usefulness of the same value when the relation is applied in additional circumstances. These three elements reinforce one another. Repetition suggests that a coefficient can be treated as fixed. Successful application elsewhere strengthens that treatment. The resulting confidence makes still broader application possible. In its proper role, constancy is therefore a method of preserving and extending demonstrated regularity. Its limitation is relational. A fixed relation between two changing quantities does not explain the conditions that keep the relation fixed. If two elements continue to vary while their ratio remains stable, something about the surrounding system must constrain their variation. That contextual structure may itself be very stable over the domain that matters to us. The mass of Earth is steady enough for vast classes of practical calculation. The mass and organization of the solar system are likewise stable enough over ordinary human timescales that treating many quantities as fixed is entirely reasonable. Alignment has no reason to discard such regularities. It changes their epistemic status. A constant becomes a record that a relation has remained stable under observed conditions, not proof that the relation is context-free or irreducible. Mathematical constants provide a concrete illustration of the distinction between a relation and the number used to represent it. Pi does not arise as an isolated quantity. It expresses a geometric relationship among circumference, diameter, and the boundary conditions that define a circle within a particular geometry. Its decimal expansion is irrational and non-terminating, as are the square roots of all integers except perfect squares. This does not make pi uncertain. It means that the exact relation cannot be exhausted by any finite decimal representation of it. In ordinary practical applications, such as machining a circular part, that distinction may be inconsequential, because the required tolerance can be established in advance, and enough digits retained to make the remaining numerical error physically irrelevant. The epistemological problem becomes more serious, when the same constant is carried into theoretical relationships, whose relevant dimensions or boundary conditions are not comparably available for direct inspection. Pi appears throughout wave mechanics, Fourier analysis, probability amplitudes, normalization relations, angular descriptions, and quantum theory more generally, often far removed from the direct measurement of a circumference and diameter. Its recurrence in such apparently different contexts may itself be evidence that those systems instantiate some common relational structure. But naming the recurring number does not identify that structure, nor can increasing the number of retained digits resolve this problem. Numerical truncation error and relational error are different things. The former can be reduced by carrying greater precision, while the latter arises when a numerical relation is applied without identifying all of the conditions that make the relation valid. A calculation can therefore employ pi to extraordinary precision while remaining structurally incomplete if the constant is standing in for relations whose determining elements have not been identified. Other irrational constants raise the same question. Their usefulness is undeniable, but their usefulness should be treated as evidence. Each successful appearance is another data point indicating that a particular relation, or family of relations, is recurring. The mistake is to allow the numerical representation to terminate the inquiry. Within an alignment approach, the recurrence of an irrational constant across different domains should increase rather than diminish curiosity about the underlying relational pattern. Because the number may faithfully preserve a relationship while revealing very little about the conditions upon which that relationship depends, or the point at which transporting it into a new context may cease to be justified. Physical constants raise the same epistemic issue in a less transparent form. The gravitational constant is an empirically determined coefficient. No current physical theory predicts an exact closed-form mathematical derivation or relates it to any other measurable elements. The numerical value assigned to the speed of light in modern SI units is exact by definition, while the physical claim concerns the invariant propagation relation represented by that number. Both are indispensable within current models because they stabilize calculations across wide ranges of application. But large-scale astronomy also shows why such stability should not be confused with explanatory closure. Galactic motions, gravitational lensing, and cosmological observations do not fit a simple accounting based only on directly visible matter, and the prevailing framework introduces dark matter and dark energy to reconcile those discrepancies. The original model for a gravitational system is applied, hypothesizing and introducing additional objects to reconcile the disparity between prediction and observation, instead of treating discrepancies as indicating flaws in the original model. The epistemic point is that the observations are already interpreted through chains of relations in which gravitational and optical assumptions are held fixed. If some supposedly universal relation were instead derivative from a broader context, even a small, unrecognized dependency could enter early and propagate through quantities inferred from it. The discrepancy itself therefore belongs among the data to be explained. It should not be allowed to protect one part of the model from reconsideration, merely because that part has worked extremely well locally. This is why constancy becomes the bottleneck rather than the error of the skeptical cycle. Testing challenges inherited explanations. Abstraction makes the resulting distinctions portable. Constancy then stabilizes the formal system so that its formulas can be reused. The success of those formulas naturally rewards the search for additional invariants, because every new constant reduces the amount of context that must be reconsidered for each application. But the same success creates resistance when a system does not fit. An anomaly can be answered by introducing another parameter, correction, hidden component, or auxiliary relation, while leaving the stabilizing constants untouched. If the amended model restores prediction, confidence in the fixed framework increases again. The cycle can therefore become negatively self-reinforcing without anyone intending it to be. Successful stabilization encourages wider application. Wider application produces anomalies. Anomalies produce additional abstraction, and the repaired abstraction preserves the original points of constancy. Alignment does not answer this by casting constants aside. It uses them differently. Their proven uses, successful predictions, domains of reliability, and failures of extrapolation all become data points for a more encompassing account. A highly stable constant is valuable evidence that some underlying structure maintains an unusually persistent balance. The more reliably the value holds, the more interesting the question becomes: what relations must remain coordinated for that stability to appear? The answer may involve elements that are themselves effectively stable over the relevant domain, or structures that current instruments cannot yet resolve. In either case, the constant remains operationally available while the explanatory question remains open. This reframing breaks the bottleneck. Instead of asking only which fixed value allows the existing formula to continue working, inquiry can ask which relational pattern explains both the domains in which the value is stable and the domains in which the larger system begins to resist the formula. Constancy then becomes what tradition became after its own correction. Not something to destroy, but something to situate. Its successes are preserved as accumulated knowledge. Its limitations identify where a broader pattern must be sought. That need leads directly to pattern matching, where the object of inquiry is no longer the single answer that continues to fit, but the structure of relations capable of explaining why it fit in the first place and when it should cease to do so. Constancy brings skeptical knowledge to a paradox. The system arose to challenge inherited claims of consistency, yet it ultimately depends upon stable formal regularities, whose deeper basis it often leaves unspecified. When an invariant fails, the usual response is to search for another variable, correction, or hidden interaction. That response preserves openness, but does not supply a principled boundary to the space of possible explanation. Alignment begins when the problem is reframed. Rather than asking what additional term will repair the model, ask what kinds of relational organization are possible in the first place. Pattern matching is the first affirmative step in that reconstruction. It does not invent order and impose it upon observation. It assumes that the recurring relations encountered by experience and the stable distinctions uncovered by testing were possible because reality was already organized in determinate ways. By learning the bounded patterns through which distinguishable elements can constrain one another, the knower acquires a new source of information, not mere recurrence and not merely experimental contrast, but correspondence between an observed configuration and a relational form that existed before it was recognized. The three subcomponents are observed relational configuration, logical pattern, and demonstrated correspondence. Observed relational configuration is the arrangement actually found among distinguishable elements. The logical pattern is one of the bounded ways those elements can constrain one another. Demonstrated correspondence is the fit between the observed arrangement and the candidate pattern. Pattern matching begins the alignment cycle by changing the object of inquiry. Repetition asks whether an event has happened before. Testing asks whether a claim survives controlled contrast. Pattern matching asks what form of relation the observed elements instantiate. The difference is decisive because the possible structure is treated as prior to our description of it. The pattern does not come into being when recognized. It is the reason recurrence could be observed and tests could produce stable distinctions before the pattern was named. This reverses the habitual direction of modern model building. Instead of collecting measurements and then searching an effectively unlimited space of mathematical descriptions, the investigator begins with a bounded grammar of possible relations and asks which pattern the measurements can occupy. This makes observation more demanding. It is not enough to say that two quantities covary. The relevant third element must be identified or its role inferred. It is not enough to say that an intervention changes an outcome. The question is how the intervention, resistance, and context form a dynamically stable arrangement. The aim is to identify topology before magnitude, the pattern of constraint before the numerical strength of each connection. Pattern matching also explains why earlier systems produced real knowledge despite their limitations. Experiential knowledge recognized stable manifestations of patterns without being able to formalize them. Skeptical knowledge isolated components of patterns and represented their regularities without necessarily identifying the whole. Alignment does not discard those achievements. It places them within the structure that made them possible. The boundedness of the pattern set matters because inference requires exclusion. If every anomaly can always be explained by adding another unconstrained factor, evidence never forces convergence. A finite grammar changes the problem. Each observation can rule out structures. Each confirmed relation reduces the remaining possibilities. Knowledge progresses by contraction rather than by indefinite expansion of explanatory machinery. This is where logical constraint becomes more fundamental than statistical fit. A curve may fit many points, but a relational pattern tells us which configurations cannot occur if the interpretation is correct. Impossibility is stronger than approximation. A theory that can say only what usually happens is weaker than a theory that can say what cannot happen without some identified structural change. Pattern matching is therefore the first stage at which consistency itself becomes an object of understanding. We no longer merely observe that something is consistent. We identify the form that makes consistency possible. That recognition establishes the basis for the next stage. Because once the pattern is known, what is not directly visible need not remain unknowable. Recognizing a relational pattern is not yet enough to make knowledge productive. Pattern matching tells us what kind of organization an observed configuration instantiates. The next question is what that organization allows us to know beyond the portion immediately present to observation. Inference emerges when the pattern has constrained the possibilities sufficiently that an unobserved relation is not merely imagined, but required by the relations already established. This is the decisive advance beyond open-ended skepticism. The unknown is no longer treated as an unlimited reservoir of possible causes simply because it is unseen. Neither is the unseen filled by traditional confidence or by formal convenience. The identified pattern determines what can and cannot occupy the missing position. Inference therefore converts structural recognition into extension. Knowledge can move beyond direct perception because the same constraints that make the observed elements intelligible also limit what the unobserved elements can be. The three subcomponents are sufficiently specified state, identified relational pattern, and necessary conditions. Sufficiently specified state is the set of known conditions adequate to distinguish the operative relation. Identified relational pattern is the structure established through pattern matching. Necessary conditions explain what else must be present if that structure has been correctly identified. Inference is the point at which alignment departs most sharply from skepticism. Skepticism treats what is not directly observed as a source of uncertainty. That caution is valuable when the possible structure is open. It becomes unnecessarily restrictive once the structure has been constrained. If the relation among the elements is known, absent information can sometimes be recovered from present information without inventing an unseen cause. This is not permission to speculate freely about what cannot be measured. It is the opposite. Inference becomes justified only when the known relations have reduced the space of possibilities enough that the missing element is required. A conjecture adds possibilities. A strong inference removes them. The confidence comes from constraint rather than from repetition or authority. This provides the basis for a new kind of faith. The word matters because every extension of knowledge beyond immediate perception requires some confidence about reality. Traditionalism places that confidence in inherited continuity. Skepticism places it in procedures that continually reopen the possibility of correction. Alignment places it in the proposition that the same relational patterns governing what can be observed also govern what cannot be observed directly. This faith is not blind because it is answerable to coherence. If an inferred element produces contradictions elsewhere, the pattern assignment must be reconsidered. If a predicted consequence fails, the system has not merely suffered an inconvenient anomaly. Some part of the inferred relation has been shown to be wrong or incomplete. Inference therefore becomes more, not less vulnerable to reality when its constraints are explicit. The practical importance is enormous. Human beings cannot directly observe every relevant state before acting. Engineers cannot destroy every structure to discover its failure threshold. Physicians cannot test every possible progression in every patient. Navigators cannot experimentally visit every possible route before departure. Knowledge becomes useful precisely because a correctly understood structure permits confident conclusions beyond the immediately observed case. The distinction from extrapolation is that extrapolation extends a fitted relationship beyond the domain in which it was measured. Inference extends a constrained relation because the structure specifies what elements are required. Extrapolation says that a pattern has continued, so we expect it to continue. Inference says that given these elements and this demonstrated organization, this consequence belongs to the same relation, unless a stated boundary condition changes. That difference restores responsibility to prediction. A model should not merely output a value. It should identify what would have to change for the output to cease being warranted. Prediction becomes an account of conditional necessity rather than a projection of past regularity. Inference therefore transforms knowledge from descriptive competence into comprehension. It is the stage at which we can act beyond direct experience without merely guessing, because we can state what makes the conclusion follow and what would invalidate it. Inference permits knowledge to extend beyond immediate observation, but that power requires a standard capable of distinguishing necessary conditions from confident error. The final stage of alignment, therefore, cannot be another form of persistence. A conclusion may endure, reproduce numerically, fit a local pattern, or generate a successful prediction while still conflicting with relations that are equally well established. If inference is to become something more than disciplined projection, the system must be able to determine when a proposed relation has actually been constrained and when unexplored alternatives are merely being ignored. Coherence provides that standard. The three subcomponents are empirical correspondence, logical structure, and systemic participation. It asks whether those can be maintained together without leaving an unresolved contradiction hidden in a parameter, exception, or inherited assumption. Empirical compatibility means that the proposed relation agrees with observation and experience. Logical compatibility means that the relation conforms to the pattern it is claimed to instantiate. Systemic compatibility means that the relation can participate in the larger organization of established knowledge without producing unresolved contradiction. Coherence requires all three because none can validate itself. In this sense, coherence completes the progression that began with repetition. Reality was first encountered as recurring, then interpreted and preserved, then challenged through controlled contrast and represented through abstraction. Pattern matching identifies the organization within those accumulated relations, and inference follows the consequences of that organization beyond what is immediately observed. Coherence determines whether the identified structure and its inferred consequences can be retained. Coherence is therefore the standard that both tradition and constancy were trying to approximate. Tradition asked whether knowledge could endure through repeated practice. Constancy asked whether a measured relation could endure through repeated application. Coherence asks a harder question. Can every relevant part of the relation occupy its place without contradiction? And can the conditions responsible for its stability themselves be articulated? That requirement establishes the boundary of alignment. Coherence cannot license necessary inference while the space of elementary relations is treated as indefinitely open. If every contradiction can always be answered by introducing another unknown kind of relation, another hidden factor, another unmeasured dimension, or another entirely new form of interaction, then no contradiction can ever become decisive. The model has not resolved the discrepancy. It has deferred resolution into an explanatory space with no stated edge. A possibility space that cannot be bounded, cannot be progressively eliminated. Aligned knowledge therefore requires more than agreement among the propositions already under consideration. It requires a bounded grammar of possible elementary relations. The narrowest claim is that once the minimum structure of a self-regulating relation, its primitive operations, and its conditions of resolution have been specified, the elementary possibility space must be finite in principle. The argument begins with what it means for three elements to be the minimum. Two elements can plainly interact. They can differ, correspond, oppose, follow, depend upon, or reciprocally influence one another. A and B can therefore describe a relation. What the pair cannot internally distinguish is its interaction from the condition regulating that interaction. If we ask what limits the relation, what permits it to remain stable, or under what condition it changes, another logical function has appeared. Without a third role, one of the two elements must serve both as a participant in the relation and as the context determining how that relation is resolved. Distinct functions have then been collapsed. A minimally self-regulating relation must distinguish three roles: an initiating condition or pressure, something against which that pressure is resisted, transmitted, differentiated, or completed, and a contextual condition within which the relation between the first two becomes determinate. These are the functions represented by A as initiatory pressure, B as countervailing resistance, and C as contextual constraint. They need not correspond to three visibly separate objects. A single object may occupy different roles at different moments. Many objects may collectively occupy one role, and a completed lower-level system may function as one element within a higher-level relation. The triad identifies functional positions, not material count. Once those positions have been distinguished, their elementary relationships can also be constrained. One condition may require another. Two conditions may be required jointly. One specified possibility may exclude another. Implication expresses necessary conditionality. If one condition is affirmed, another must also be affirmed for the stated relation to hold. It does not by itself assert causation, temporal succession, or independence from a shared cause. Conjunction expresses joint conditionality. Two elements participate together in satisfying a requirement that neither independently exhausts. Exclusive disjunction expresses constrained alternatives. One of two specified possibilities may hold, but not both. Together, these operations represent directed requirement, cooperative requirement, and exclusive determination without opening the system to an unlimited vocabulary of primitive relations. A qualification is necessary. A finite relational vocabulary alone does not guarantee a finite number of expressions. A small alphabet can produce sentences of unlimited length. The elementary unit must also be bounded. Triads offer the necessary framework. An elementary pattern is a completed organization of three functional roles whose three relations can be assessed together as one system. Longer constructions are compositions rather than new elementary forms. A completed triad may become an element within another triad. Several triads may join into a higher order structure, and the same relational form may recur at different scales. This distinction between elementary form and recursive composition allows boundedness and complexity to coexist. A language does not require a new grammatical rule for every sentence. Music does not require a new interval for every composition. Computation does not require a new logical value for every program. In the same way, a bounded relational grammar can generate extraordinary complexity through nesting, combination, repetition, and reorganization. The epistemological progression developed here already demonstrates that principle. Repetition, interpretation, and tradition form one larger system. Testing, abstraction, and constancy form another. Pattern matching, inference, and coherence form a third. Those three cycles then become elements considered through association, and their surviving capacities are joined through integration. The output of one level becomes an element at the next. Complexity grows recursively, while the underlying relational functions remain recognizable. Coherence, therefore, does not require us to claim in advance that every possible pattern has already been catalogued. It requires the narrower and more important proposition that the elementary space is bounded in principle. If the functional roles are limited, the primitive relational operations are limited, and an elementary pattern is defined as a completed organization rather than an indefinitely extensible expression, then elementary relational possibility cannot remain infinite. This distinction makes the theory testable without leaving its explanatory space indefinitely open. If another primitive relational form is required, its distinct function must be identified. What does it express that necessary conditionality, joint conditionality, exclusive alternatives, and their organized combinations cannot represent? What additional role does it perform within a self-regulating relation? Merely asserting that some entirely different relation might exist preserves abstract possibility, but it adds no explanatory content. A constrained epistemology should require the missing function to be articulated, rather than grant unlimited explanatory freedom by default. Bounded relational possibility also clarifies the difference between resolved and unresolved states. An affirmed configuration is one in which the relational requirements converge upon a common positive state. A negated configuration is the complementary organization through which absence, reversal, failure, or exclusion resolves into a common negative state. A configuration containing incompatible requirements is not an additional stable pattern, merely because it contains a mixture of affirmed and negated elements. It is unresolved. Unresolved does not mean unreal, and dynamic balance does not mean motionlessness. A changed element may place pressure upon the others. They may compensate for it, change state with it, oppose it, reorganize their relationships, or force a transition into another resolved configuration. Where one discordant element is maintained by an external condition, its value can propagate through the progression of the pattern's requirements until the remaining elements resolve in relation to it. The affirmative and negative forms describe resolved organizations. Mixed states describe disequilibrium, transition, or unresolved constraint. The elementary patterns are distinguished by the organization through which balance is maintained, lost, or restored. This gives contradiction a more useful epistemic meaning. Under traditionalism, an anomaly may be absorbed into interpretation or dismissed as an exception. Under skeptical formalism, it may motivate another parameter, correction term, hidden factor, or restricted domain. Under coherence, contradiction means that at least one asserted relation cannot remain as currently understood. If context resolves the contradiction, the contextual element must be identified. If a threshold changes the relation, the threshold belongs in the account. If two observations belong to different relational organizations, the boundary between those organizations must be made explicit. Contradiction may be resolved, but it cannot merely be renamed. Empirical compatibility remains necessary because a logically elegant relation that never appears in experience is not knowledge of reality. Logical compatibility remains necessary because repeated observations can be organized by an incorrect interpretation. Systemic compatibility remains necessary because a local relation may work while contradicting equally established relations elsewhere. None of these standards can validate itself. This prevents mathematics from using itself as its own evidence. Internal mathematical consistency establishes that a representation can coexist with its assumptions. It does not establish that the represented relation exists materially. Likewise, empirical recurrence establishes that something happens consistently. It does not establish that the proposed structure explains why. And successful integration with a larger model cannot compensate for an interpretation that lacks correspondence with observation. Coherence requires the bridges among these forms of consistency to remain visible. The bounded character of elementary relation is what allows these tests to become genuinely discriminating. If relational possibility is indefinitely expandable, every contradiction can be answered with another hypothetical structure, and evidence can never force resolution. Within a bounded grammar, observations can eliminate incompatible organizations. Further observations can distinguish among those that remain. Established relations can constrain the possible role of something not yet directly observed. As knowledge increases, the field of coherent explanation contracts. This is what allows pattern matching to become more than analogy. A recognized pattern matters because it carries constraints. Once a system has been identified as instantiating a particular relational organization, not every subsequent state remains equally possible. It is also what allows inference to become more than extrapolation. If relational possibility were fundamentally open-ended, an unobserved element could always participate in some relation not yet imagined. We could estimate what probably occurs from precedent, but necessity would remain inaccessible. Within a bounded grammar, sufficiently established relations can eliminate alternatives until the unknown is constrained by the known. Coherence polices that progression. It prevents pattern matching from becoming imaginative resemblance and inference from becoming overconfidence. A proposed pattern must fit what is observed, remain internally consistent, and participate without contradiction in the larger organization of demonstrated relations. The boundary conditions within which it holds must be stated, and the observations that would force its revision must remain identifiable. If it fails any of those requirements, the pattern has not been established strongly enough to support necessary inference. The result is a stricter standard for confirmed knowledge. A claim is not secure because experts agree with it, because a model fits the data, because a parameter has been measured precisely, because a formula has remained useful, or because a prediction succeeded. These are all evidence. None is sufficient alone. The relation must correspond with observation, instantiate an intelligible pattern, and join the larger network of established relationships without requiring unexplained exceptions to preserve it. Coherence therefore completes the alignment cycle in a stronger sense than confirmation. Pattern matching identifies a constrained relational possibility. Inference follows the consequences of that structure beyond what is immediately observed. Coherence determines whether the identification and its consequences can remain part of an integrated body of knowledge. Because coherence requires the elementary possibility space to be bounded, each successful determination reduces what remains possible rather than merely adding another successful description. That is the form of confidence alignment seeks. Not certainty without correction and not correction without end, but progressively constrained understanding in which fewer incompatible organizations remain. Coherence is both the standard of aligned knowledge and the boundary that makes alignment possible. Without bounded relational possibility, pattern matching remains resemblance, and inference remains sophisticated induction. With it, observation can eliminate possibilities, contradiction can force reorganization, and established relations can constrain what has not yet been directly perceived. Knowledge advances from recognizing that reality behaves consistently to understanding the relational conditions through which that consistency is maintained. Coherence completes the third epistemic cycle, but completing alignment does not erase the history through which it became possible. The experiential and skeptical systems each developed capacities that alignment depends upon. Direct recurrence, practical interpretation, preservation, deliberate testing, abstraction, and measured invariance all supplied information that made the recognition of deeper relational patterns possible. The task now is to reconsider the three systems together, without allowing any one of them to define the others by its own standard. This is the work of association. At the top level, the three concepts occupy distinct roles that must not be confused with their temporal sequence. Experiential knowledge is the initiatory pressure to articulate the world. Skeptical knowledge is the countervailing resistance generated when that articulation proves incomplete. Alignment is the contextual structure that makes both intelligible by identifying the patterns within which their partial successes and failures occurred. Association determines what each system genuinely contributed and what must be discarded before their contributions can be combined. The three top-level concepts are experiential knowledge, skeptical knowledge, and alignment. Experiential knowledge is the initiating effort to articulate the world through repetition, interpretation, and tradition. Skeptical knowledge is the countervailing resistance that corrects those interpretations through testing, abstraction, and constancy. Alignment is the contextual understanding that becomes possible through pattern matching, inference, and coherence. These concepts must remain in their actual temporal order. Experience comes first. Skepticism arises because experiential interpretation encounters contradiction. Alignment comes later because the accumulated insights of both prior cycles are required before the structure that made their partial successes possible can be recognized. But temporal discovery must not be confused with ontological creation. Alignment is discovered last. The patterns it identifies were operating from the beginning. Association is therefore not compromise. It does not average tradition and skepticism into a moderate position. It asks what each system was responding to, what genuine capacity it developed, and which distortion arose when that capacity was mistaken for a complete account of knowledge. From the experiential cycle, we preserve natural observation, practical consequence, embodied interpretation, accumulated skill, and the conviction that reality exhibits consistency. We reject the assumption that repeated success validates the interpretation attached to it. Tradition remains a means of preservation, not a final court of truth. From the skeptical cycle, we preserve deliberate discrimination, controlled comparison, symbolic portability, measurement, error correction, and reproducibility. We reject the assumption that staged experimentation exhausts legitimate observation, that mathematical representation is equivalent to explanation, and that invariance measured across an accessible domain becomes universal merely because no deviation has yet been detected. From alignment, we gain the context in which these contributions stop appearing contradictory. Experience was able to accumulate knowledge because stable relational patterns existed. Skepticism was able to correct experience because interpretations of those patterns could be wrong. Formal abstraction was able to travel because some relational features genuinely persisted. Formal abstraction also failed when it compressed or omitted the context responsible for that persistence. Association therefore validates by preservation under explanation. A component from an earlier system should be retained when alignment can show what function it performs and what conditions make that function reliable. A component should be revised or discarded when it depends upon a contradiction that cannot be reconciled with the larger structure. This is a more generous and more demanding treatment of intellectual history than declaring one age enlightened and another superstitious. People were generally trying to solve real problems with the epistemic tools available to them. Traditional societies needed continuity. Experimental science needed correction. Mathematical science needed portability. Institutional science needed coordination. Each solution became distorting when the mechanism designed to solve one problem was elevated into a universal standard. Association is the point at which those distortions can be separated from the capacities that produced them. It allows knowledge to advance without requiring historical amnesia. The future does not need to destroy the past. It needs to understand what the past was actually doing well enough to preserve its valid functions without preserving its mistakes. Association resolves the false opposition among the three epistemic systems, but preserving their valid contributions is not yet the same as possessing one method of knowledge. Integration is the point at which the progression becomes operational as a whole. The capacities discovered successively through the experiential, skeptical, and alignment cycles must now be re-identified as parts of a single process that can obtain knowledge, use it, test its adequacy, preserve it, and transmit it without reproducing the limitations of the stages from which those capacities emerged. The 9 unified concepts are repetition, interpretation, tradition, testing, abstraction, constancy, pattern matching, inference, and coherence. Repetition is the capacity to recognize recurrence. Interpretation is the capacity to assign practical meaning. Tradition is the capacity to preserve useful knowledge. Testing is the capacity to distinguish competing interpretations. Abstraction is the capacity to make relationships portable. Constancy is the capacity to identify stable regularities. Pattern matching is the capacity to recognize relational structure. Inference is the capacity to recover necessary conditions from constrained relations. Coherence is the capacity to confirm that knowledge remains compatible across observation, logic, and system. Integration does not simply place these 9 capacities in a sequence. It reorganizes them into 3 complete functions of knowing, obtaining knowledge, applying knowledge, and making knowledge teachable. Obtaining knowledge integrates repetition, testing, and pattern matching. Repetition keeps inquiry anchored in naturally occurring recurrence. Testing introduces deliberate discrimination where interpretations conflict. Pattern matching determines which relational structure accounts for both the recurrence and the discriminating result. Observation is therefore neither passive experience nor laboratory production alone. It is the progressive identification of structure through naturally occurring and deliberately selected evidence. Applying knowledge integrates interpretation, abstraction, and inference. Interpretation gives the relation practical meaning. Abstraction makes that meaning portable beyond the original encounter. Inference determines what may legitimately be concluded beyond direct observation. The 3 together prevent 2 opposite failures: action based only on inherited intuition, and calculation based only on symbols. Application becomes informed action, grounded in a relation whose implications are understood. Making knowledge teachable integrates tradition, constancy, and coherence. Tradition preserves what has been learned. Constancy supplies stable reference points that make knowledge reproducible. Coherence ensures that what is preserved and reproduced can still be reconstructed as an intelligible relation. Teaching therefore ceases to be the transmission of conclusions and becomes the transmission of reconstructible understanding. This distinction is essential. A person can memorize a formula, procedure, rule, or accepted conclusion and reproduce the expected output under familiar conditions without understanding the relation involved. Such competence is useful, but it is not integrated knowledge. The test of teachability is whether another person can recover why the relation has the form it does, what conditions make it applicable, what competing patterns were excluded, and what change would require the conclusion to be reconsidered. Integration also gives us a standard for institutions. Schools should not reward the reproduction of authoritative statements when the underlying relation cannot be reconstructed. Scientific disciplines should not treat technical fluency as equivalent to comprehension. Engineering should not accept successful interpolation as sufficient evidence for extrapolation into a new regime. Public institutions should not convert expert consensus into a substitute for explaining the constraints that justify action. The integrated system is not hostile to expertise. It demands more from expertise. An expert should be capable not merely of operating the formalism, but of identifying the relevant elements, explaining the pattern of their interaction, distinguishing measurements from assumptions, stating the domain in which the relation has been confirmed, and identifying what evidence would force a structural revision. Knowledge becomes durable under this model because preservation no longer depends upon obedience. It becomes portable because abstraction no longer has to pretend to be reality. It becomes predictive because inference no longer depends upon blind extrapolation. It becomes corrigible because coherence makes contradiction actionable rather than embarrassing. Integration brings the 11-stage progression to completion, but its purpose is not to leave us with another theory to admire. A theory of knowledge matters only if it changes how knowledge is sought, recognized, used, and taught. The practical path forward begins with two problems that the preceding account has made visible. The first is fragmentation. Human understanding has been divided into disciplines, vocabularies, methods, and professional territories that often describe different instances of the same relational problem without recognizing their common structure. The second is unfamiliarity with patterns themselves. We are trained to remember facts, formulas, classifications, and procedures, but rarely to recognize the recurring forms through which influences combine, resist, reinforce, constrain, and balance one another. Alignment addresses both problems at once. It reunifies knowledge by making relational pattern the common language through which otherwise separate fields can be compared. This does not require inventing an entirely new intellectual culture. It requires recovering a capacity that human cultures cultivated for much of history. Myth, scripture, philosophical teaching, esoteric tradition, drama, parable, genealogy, law, and practical craft repeatedly preserved knowledge in stories about relationships. The objects changed, rulers and advisors, parents and children, rivals and allies, gods and mortals, hunger and abundance, loyalty and betrayal, order and disorder. Yet beneath those changing objects, the same kinds of relational structures recur. Stories endure partly because they make patterns memorable. A narrative can preserve how three pressures interact long after the original circumstances have disappeared. The story need not be a literal report of an event to function as a model of relational possibility. Its value can lie in making a pattern visible enough that it becomes recognizable elsewhere. Pattern recognition requires familiarity. One does not learn a language by memorizing a definition of grammar and then expecting immediate fluency. One encounters many sentences until recurring structures become perceptible. The same is true here. The triadic patterns can be stated abstractly, but abstraction alone does not make them usable. They become usable through repeated encounters with concrete examples. Read a story and ask what initiates movement, what resists or redirects it, and what contextual condition makes the relation intelligible. Read another story with different characters and circumstances and ask whether the same structure appears. Compare a political conflict with a family dispute, an ecological balance with an engineering failure, a market cycle with a biological feedback process. The objects may have almost nothing in common. The relational organization may be the same. With enough exposure, recognition becomes faster, more precise, and less dependent on surface resemblance. This is the practical meaning of a rebirth of knowledge. The enormous archive of human thought becomes more than a collection of doctrines competing for assent. It becomes a training ground in pattern literacy. Earlier traditions do not have to be accepted wholesale, romanticized, or treated as infallible. Their stories and models can be examined as accumulated attempts to represent recurring relations. Modern scientific knowledge can be approached in the same way. A formula, constant, experimental result, engineering rule, or statistical regularity is not discarded because its explanation is incomplete. It becomes another data point. We ask what it reliably captures, under what conditions it has worked, where it begins to fail, and which larger relational pattern could account for both its successes and its limits. The purpose is not to replace one canon with another. It is to learn how to extract structural information from every source without confusing the source with the structure. Education would therefore change first. Students should still learn facts, mathematics, experimental technique, history, and established models, but these should be organized around comprehension rather than reproduction. A student encountering a law or formula should learn not only how to use it, but what observations it condenses, what relationships it presumes, what context keeps those relationships stable, and what kinds of change might make the approximation fail. A student reading history or literature should learn not only themes and dates, but how recurring structures of reinforcement, resistance, dependence, convergence, division, and integration organize events. The same pattern encountered in several domains becomes easier to recognize in a new one. Knowledge then stops being a warehouse of separate answers and becomes an increasingly connected capacity to understand unfamiliar situations. Scientific practice must change in the same direction. Experiments remain valuable, but their highest purpose is discrimination among relational possibilities, rather than the accumulation of isolated measurements. Constants and formulas would remain useful records of stable behavior, but their successful predictions would be treated as evidence to be explained within a more encompassing structure. An apparent exception would not automatically demand another adjustable factor, nor would it simply overthrow what previously worked. It would identify the location at which the existing relational account is incomplete. The question would become, what additional element or nested triad makes both the previous regularity and the new discrepancy coherent? In this way, the older model is preserved as a local description while becoming evidence for a larger one. Progress does not require throwing away what worked. It requires understanding why it worked and where it belongs. This also offers a remedy for fragmented expertise. Different disciplines can retain their specialized measurements and techniques while becoming mutually intelligible through shared relational forms. A physicist, biologist, historian, engineer, psychologist, and political theorist need not share the same objects of study in order to recognize the same pattern of reinforcement or bottleneck, the same convergent dependence, or the same failure of integration. Cross-disciplinary work then becomes more than borrowing metaphors or combining datasets. It becomes comparison at the level of structure. A pattern established clearly in one domain can suggest what relationships should be looked for in another, while differences between the cases reveal which contextual elements matter. That is a practical form of inference, not because one discipline dictates conclusions to another, but because a known relational grammar helps identify what evidence would discriminate among possibilities. The final change is cultural. Knowledge no longer needs to define itself by opposition to tradition, skepticism, religion, mathematics, intuition, or experiment. Each of these can be understood as preserving part of the human effort to make reality intelligible. The question is not which institution or historical system deserves final authority. The question is what relational understanding survives when observations, interpretations, tests, abstractions, regularities, patterns, inferences, and larger systemic consequences are brought into coherence. That standard is demanding, but it is also liberating. It allows confidence without dogmatism, because confidence rests on constraint. It allows curiosity without permanent doubt, because an unresolved question points toward relations still to be identified. It allows inheritance without submission, because what is received can be reconstructed and tested for coherence. The rebirth of knowledge therefore begins with a simple discipline. Learn the patterns, look for them everywhere, and refuse to confuse their temporary representations with the relations themselves. Recover the stories through which earlier cultures made patterns memorable. Study the formulas through which modern science made regularities portable. Treat both as records of encounters with the same consistent reality. Then compare, distinguish, infer, and integrate. The more patterns a person understands through varied examples, the more readily unfamiliar circumstances become intelligible. What first appears unprecedented can often be recognized as a new arrangement of familiar relations. What appears mysterious can be approached by asking which element is missing. What appears contradictory can be examined for a larger context in which the contradiction resolves. The result is not the abandonment of accumulated knowledge, but its reunification. Experience recovered from traditionalism, discrimination recovered from skepticism, and both brought into alignment through an explicit understanding of the patterns that make knowledge possible.